Okay, we're back for the next installment of Endless Energy and Meteorology. So this is the next topic over the big picture of how the weather works. So let's get kicked off with this mini lesson today. Let's look at the major variables that are associated with weather. So meteorologists, like the people you see on TV, you know, in the morning at CBS or ABC or Pix 11 or whatever you're getting your weather from, tend to focus on these four major variables when predicting the weather. So the first one you're going to probably hear them talk about is air temperature. That one goes without saying. I mean, almost every day you're going to look at the air temperature to decide whether or not today is going to be a nice day to wear those nice shorts or t-shirts, or if you're going to be bundled up in a jacket and a scarf with a hat on as you walk to school. Dew point temperature, you've probably heard of it, but may not be as familiar with why that's important, but we'll get to that. Humidity, I mean, I think the easiest way to relate to humidity is when it's hot outside, it feels muggy, okay? You feel like you can see the fog in the air. Those are days that have high humidity, but there's also days that have low humidity, and we'll talk more about that. Also, wind speed. That states for itself. I mean, wind speed, how fast the wind is blowing, how slow or fast, depending on what type of weather system you have coming in, and also just air pressure. Air pressure is going to help us understand wind. It's also going to help us understand whether or not we're going to have a clear day or we're going to have a stormy day. It's going to we're going to understand more about how the air pressure affects things like hurricanes or tornadoes, or if we're expecting to have maybe a beautiful stretch of clear days, which as of right now definitely is not. So, however, we are in the season for that. Let's talk about air temperature changes and what affects the daily cycle, the seasonal cycle. All right, so normally if we're talking daily, it's pretty obvious for most of us that we know that it's colder in the morning. So typically around your 5 to 6 a.m., depending on if your daylight savings or standard time, but between that period of time is when we have cooled off furthest from when the sun has set. So when the sun sets, our energy source is now gone. The heat source that we talked about a few topics ago, but that heat source goes below the horizon as we rotate away from it, and then we start to cool down. Whatever ambient heat has been absorbed by the earth, the ground, the plants, the people, the cars, all that starts radiating away back out into space and beyond some of our atmosphere, which causes us to gradually cool down. And when we get to 5 or 6 in the morning, that's just before, or roughly close to just before, when sun is going to rise again and reheat up everything on our planet. So our daily cycle, usually coldest around 6, usually warmest around 3 p.m. because there's a little bit of lag time between the amount of heat being absorbed at noon, along with that sun staying in the sky, allowing the ground to continue heating up until maybe our sun's insolation, that angle of the sun, is decreasing as it's about to set, and then we start to hit peak heat and drop off from there. Now, superimposed upon every daily cycle, we have things like clouds. Okay? And most of you realize that the clouds kind of look gray from underneath, but that's because we're beneath them and they're causing a little bit of an overcast, a shadow. But if you're above those clouds, if you've ever been on a plane before, you can see that at the top of those clouds, they are bright white, almost so bright sometimes that when you look down, you might even need sunglasses on while you're in the plane. Right? So regional air masses impact our daily temperatures. Right? On a seasonal aspect, our Earth is tilted. Let's grab the prop. Earth is tilted 23.5 degrees, so depending on where we are going around the sun, the angle that we are tilted at will impact the angle of the sun. So if we are tilted away in the northern hemisphere, we're not going to get those intense rays of solar heat coming to us. So it's going to be winter in those instances. But if we were to disregard what I just did by turning the sun around, when we get to astronomy, we'll talk more about that. But when we are tilted towards the sun, we're going to get more direct radiation, and we're going to be warmer like the summertime. So all of those different aspects develop our system of climate and our seasonal and our daily temperature changes. All right, what causes air pressure? Well, What most of you don't realize right now is that as we're standing here, there's pressure being pushed on our bodies, which are keeping them together and preventing us from going exploding. So that's why when you're in outer space, you need to be in a pressurized vessel. That's also the reason why planes are pressurized from the inside, to help prevent all of that stuff from happening. Now, the amount that we've been able to measure is about 14.7 pounds of pressure per square inch of your body. I don't know how many of you are familiar with bowling, or you like bowling, or you've held a 14-pound bowling ball, but pretend for a moment that you thought that there was a 14-pound bowling ball on every square inch of your body. Can you imagine how much pressure is being exerted upon you? And then you say, Mr. Ryan, well, how come I can't feel that? Well, that's because we as human beings have always adapted to this air pressure, and so we're not feeling all the extra pressure of the air on us. That's what's holding us together from falling apart. Now, if you go to outer space and you're lacking that 14.7 pounds per square inch, you're probably going to be, let's just say, you ever see the confetti explode? Maybe like that, and then you freeze. It's kind of like a poof, and then you freeze, right? So it's all that vapor pressure stuff that's out there that's missing, all right? A barometer on our planet here is what we use to measure the variability as air masses move through, and they're either bringing in more pressure from more air, or you have a system bringing in maybe less air. And so that pressure is going to vary depending on how much is pushing down or moving away from us, okay? Now, a barometer, for lack of a better example right now, and you're welcome to YouTube a video on a barometer, but a barometer here, we tend to have a vertical column or a vertical tube that's turned upside down, and inside you have this fluid. It could be an alcohol, it could be a mercury. Most of the time we move away from mercury because it's dangerous, but if the air becomes heavier because more air pushes into the area, the mass of air is going to push down on this fluid, and it's going to push that fluid up the column. And as that column rises, we say we have high pressure. Now, if we have low pressure coming in, there's going to be less air above this pool of fluid, and it's going to release that pressure, allowing the fluid in this column to reduce or drop. And that indicates low pressure. So a barometer is going to be our tool to measure air pressure. Okay? Now over here we have altitude above sea level and air pressure. So the further you go to outer space, the less air you have. So that means you're going to have lower air pressure. So if we're at sea level, let's just say for now, you have higher pressure because there's more air above you. But as you move closer to space, you're going to have less and less pressure until there is no pressure and you're in a vacuum. All right. Now, one of the things that I like to point out is if you're ever in a sports stadium, some of the biggest records of home run hitters or field goal kickers, or even in terms of just like a goalie kicking the ball down the field, you're going to have a better opportunity to make those records in places that are up in high elevation because there's less air resistance, because there's less air. Check those out. All right, so moisture in the air. Let's continue the process to talk about another variable that we have to look at, being moisture. Okay, so depending on the temperature in the air, air holds a certain volume of water, and it's going to be water vapor. Okay, now as the temperature rises, every 10 degrees Celsius, we do have a doubling amount. There's an increase by double the volume that the air can hold. So that's why in the summertime it tends to feel more humid, because the air is warmer, and that warmer air can hold more water vapor in between its molecules. So when the air expands, because it's less dense, more water vapor can fill into that space in between. So it tends to feel more moist, more humid. But when we talk about the seasons like the winter that we're in now, temperatures, well, coming out of winter, but in winter those temperatures are cooler, so there's less space to fill up with water vapor, so it tends to be drier. Okay? Dew point temperature. So at this temperature, this is the temperature the air has to cool down to in order for water vapor to condense. Okay? So once you hit dew point, you have completely saturated the air. Okay, so what does that actually mean? So how about we get a few little props here, and I can kind of point out exactly what I mean by that. All right, so if we were to look at these particular items, okay, we'll say each of these containers represents water vapor. And my hands, my fists, just like in our density example of neutral hands, density sign language, they're going to be air molecules, okay? So in order for this gas to turn back into a liquid, my air molecules need to cool down until it gets to a point where well, I'll explain what I just did there. So as the air cools down, it will cause less space to be available for that water vapor to float around. And it starts to lose heat and recombine into a liquid. And eventually, once you hit dew point temperature, which is where you can't squeeze down that water anymore, that water turns into a liquid and rains. Right? So the main thing we're going to be talking about is air temperature and dew point temperature to start with, so that we can start to identify what is that temperature at which water vapor is going to condense into a liquid and maybe become precipitation. Okay? So what I'd like you to try to do is I'd like you to try to answer this yourself as a stop and jot, a place for you to start thinking. So what happens to the density of gas as it cools? We just spoke about that. And then how could you create an example of how a sponge, maybe a wet sponge, not a super wet sponge, might actually be a good example of how air temperature and dew point interact with one another, like the containers for the example. So pause, think about that for a moment, maybe jot something down in your own words. Okay, so if you've had an opportunity to try to answer that question, let's kind of look at that from a perspective that we have. So if we've got a sponge here, if we've got this sponge here that fills up with a little bit of water, that sponge represents air temperature. So there's space in between all of the fibers of the sponge for water to start filling in. Okay? Now, in order for us to represent something like precipitation, maybe the air temperature starts to cool down and the air gets closer together. And think about when you're squeezing a sponge and you're reducing the amount of airspace, that eventually you get to a place where you start to squeeze out the water in the sponge. And that point at which you're squeezing the water out of the sponge, you can call that the dew point temperature. Okay? So that's yet another example for you to be able to kind of identify the relationship between air temperature and dew point temperature. All right, so in order for us to start measuring the dew point, we have to use a device called a sling psychrometer. So these are two thermometers hooked up to a handle that you're going to swing around until you record a difference between them. A difference that is recorded due to the evaporation of water on this thermometer. So there are two thermometers. Let's break down what those two thermometers are going to do. One thermometer does not have anything at the end of it. It is reading air temperature. Thermometer number 2 has a small little sock on it. And we dip that sock in air temperature water. So water that has been able to come up to room temperature, also known as. We dip it in there so that there's no change in temperature between the two thermometers. We then take the psychrometer and spin it around until we've evaporated as much water as we can from here. Because as we evaporate water, we're putting heat into that water, and then that water is going to leave, taking the heat away with it. And as there is room in the air for that water to evaporate into, it's going to reduce the temperature of this wet bulb thermometer. That is recording the temperature of evaporation. We then use the difference between those two temperatures to calculate dew point. Fortunately for us, our reference tables give us a chart and will tell us how to calculate dew point and relative humidity from the dry bulb, which is air temperature, and the wet bulb that records the temperature of evaporation. You can also think of how you feel cooler when you're running around playing basketball or jogging or running or playing softball, and whatever physical activity you're doing, you generate sweat, either on your face or your arms or your back, and then when a cool breeze comes through across you, it makes you feel cooler too, because not just as cool as the breeze, but also it's taking and evaporating that water away. So it's taking the heat in that liquid and pulling it away from you. So you can think of this almost as if like this is sweat evaporating off the wet bulb and it's cooling it, all right? So let's keep going. Now we want to make sure we understand how the difference between these bulbs will impact our prediction of weather. So here, if we have more water evaporating into the air, there must be room in the air for there to be water evaporating. So it will have a big difference. Lots of evaporation pulls a lot of heat away from the wet bulb. If it is a very humid air, if it's very humid air, you will expect very little evaporation to occur because most of that air is already full of water vapor. So let's take a moment, let's read through this together, and then let's go and take these examples and understand how we use the reference tables to solve this. Okay? So, page 12 of the reference tables. I've got mine open. Do you have yours open? Make sure you get there. Let's follow the procedures below to accurately solve for dew point temperature. So, record the wet and dry bulb temperatures. That's important. Subtract the two temperatures. Find the dry bulb on the left column of the chart. You're then going to use the subtracted difference to find your value on the top of the chart. Follow across and down from each number until they intersect on a dew point temperature. Let's take this and this information for our first example, 15 degrees C wet bulb, 20 degrees C dry bulb, and let's walk through these procedures but on the reference tables. So wet bulb was 15 degrees C, dry bulb 20 degrees C. So as we were spinning a sling psychrometer around, we recorded a 5 degrees Celsius difference, meaning that there was room within the atmosphere for those water molecules to evaporate and fit into the air. All right? So let's look at this so we understand how to use those pieces of data. So difference between wet bulb and dry bulb temperatures. That sounds to me, the word difference, if you recall, subtraction. So we're going to be subtracting between the wet bulb and the dry bulb temperatures. Cool. Dry bulb temperature, AKA, and add this to yours as an annotation every now and then, this is just air temperature. Okay? It's nothing fancy, but we call them dry bulb versus wet bulb because of the device we're using, which is a sling psychrometer. Okay? So first things first, our dry bulb was 20 degrees C. So let's look and find 20 degrees C on this far left column. Here's 20 degrees C. Next, we have to do the difference. You're not just taking 15 degrees C and going to that column. You need to process your values before utilizing one of these columns. So we've got difference between wet and dry. So we subtract the 2, we get a difference of 5. If you choose to, in this case, to take wet bulb and subtract dry bulb, you end up with a negative. I will say for the purpose of this, use the absolute value. Drop the negative, find the column you need to use. So we're going to be using a difference of 5 degrees Celsius. So we come down and we find where the two of them are going to intersect. And it looks like we have a dew point temperature. So I'm going to call it DPT. That's not accepted anywhere else except in your notes. DPT, dew point temperature of 12 degrees Celsius. So in order for it to rain or snow, depending on whether we're above or below freezing, we have to cool our air temperature down to 12 degrees Celsius to condense liquids in either the form of fog, the form of rain, or the form of snow, depending on our temperatures above or below freezing. So in this case, we'd have to cool down to 12 degrees C before it were to rain, because 12 degrees C is above 0, which is freezing. If this were 0 or less, then maybe we'd have the chance for freezing rain, maybe snow or sleet. Okay. So that's our first example. What I'd like you to do now is I'd like you, that's the same value. Let's change that up. Let's just make this 10 degrees C. Okay, so for you, go ahead and try this one out. 10 degrees C for the wet bulb, 20 degrees C for the dry bulb. I want you to pause the video and try this out using your reference tables. All right, so we have a wet bulb of 10 degrees C and a dry bulb of 20 degrees C. That's a bigger difference, meaning that there was more evaporation into the air. And if there's more evaporation into the air, there was more room in the air, meaning that the air must have been drier. So we have a difference of 10. So here's our difference of 10, same air temperature, so same dry bulb on the column, and identify that they will be, sort of that a little better, -2 degrees Celsius. That's below freezing. So if a cold air mass moved in here very quickly, then we might say that if this temperature could drop down to that, you might get frost, you might get a little snow, you might get a flurry. Okay? The bigger these gaps are though, usually the harder it is for that to drop. It's not impossible, but usually we like to see there to be a closer difference in order for it to be imminent for there to be any type of precipitation. Okay. All right, let's continue. We got to talk about relative humidity, which works the exact same way. All right, so relative humidity is expressed in the percentage of the amount of water vapor that's actually in the air. There are two aspects to humidity. There is the relative humidity based on the current conditions, and then there's absolute humidity. Excuse me. All right, so they're both expressed the same way. We use the chart below, which looks very similar, and we process our data the exact same way. We also use the same two numbers that come off of the sling psychrometer. So here we've got an example. We got a dry bulb of 14 degrees C, wet bulb of 9 degrees C. Do a quick check again, just to make sure. 14 for dry, 9 for wet. All right, so we've got our data. 14 degrees C is here. 9 degrees C is not the column. We, again, difference between wet bulb and dry bulb. So we subtract the 2. We get a difference of 5. So relative humidity is at 50%, meaning based on these temperature conditions, the air is half full of water vapor. Now, as the temperature increases, you may also have an ability to hold more water. So if I were to have this container full of these 10 pencils, if I were to then say, okay, this container is maybe 10 degrees Celsius, okay? So 10 degrees Celsius is holding all of these, and let's say it's taking up 30% of the air space. Well, if that air temperature increases and I don't get any more water vapor, Now maybe that water vapor only takes up 10% if the air temperature increases with no new moisture. That water is going to take up less space in the air than it did before when it was cooler. We may also end up in a situation where maybe we have our air with maybe 25% full of water vapor. And then more moisture comes in due to a weather system. The temperature may not change, but if more moisture is added to the air, now you have a higher percentage of the air that is full of water vapor. So under those two conditions, let's take a look at these examples and see how each of those models is represented by these pictures. So here we have originally 0 degrees Celsius and the temperature gets higher. But I have not changed the amount of water vapor. So we're in the condition where we had the smaller container at 0 degrees C, and it was we could pretend in this example it's completely full. But if the temperature increased to this bucket, it's now bigger. And whatever was in here that filled all this up is no longer enough to fill all of this container or air up. So the percentage of humidity drops. Okay? So that means in this case, we're dealing with relative humidity. The one below is going to be dealing with absolute humidity, which is what we were talking about originally when we had airspace with some moisture in, but that temperature didn't change. And then we added more water vapor to the system. So we have our container with just a few colored pencils in it, but then more moisture showed up in the air and we added more pencils, but we've never changed the temperature for the air. And one last thing to close out before we choose to do some practice together. And I want you to add this to your notes too, anywhere you are taking notes, whether it's in this document or maybe somewhere else that you're annotating. But when air temperature is close to dew point temperature, the air is almost saturated. That means relative humidity is close to 100%. That means it's going to be close for precipitation. So that 0 to 1 degree difference between temperature and dew point indicate to us that we have high chances of precipitation. Okay? So just to reiterate, the fact of the matter is, if you have an air temperature that is close to dew point, you are getting close to filling all of the airspace with water vapor. And if it's only a couple of degrees off, you should expect it to become more saturated, close to 100%, and a high chance of precipitation. All right, so if you are on the digital aspect and you didn't get a packet because I wasn't able to get them to you, we're in the weather folder. And within the weather folder, we are looking at relative humidity and dew point. We want to open up the relative humidity and dew point practice, this one here. So you want to bring this up on your screen so that we can practice this together. You may need the relative humidity and dew point axis point, so pull that up and add those as tabs on the side so you can do some work elsewhere. All right, let's go back to the notes. All right, so let's work on question 1 and 2 for guided practice. Pause the video, give them a shot. You have some resources, let's see what you can do. Okay, I hope you've come back and you've actually given this a shot. I don't think it's that intimidating. You've got a lot of great resources to use. So the data table below shows the dry bulb and the wet bulb temperatures measured with a psychrometer on 4 different days at the same location. So same location, we've got dry bulb, wet bulb. We've got day 1, day 2, day 3, day 4. We've got dry bulb air temperature. We've got wet bulb temperature of evaporation. Okay, this is according to the data shown in the table, which day had the highest relative humidity? Well, kids, I think we're going to have to try to solve these a little bit. All right? So let's get some information below, get some data, and try to figure this thing out. So I am going to grab my reference table so that we are looking side by side together and we are not jumping back and forth on the screen. So we are on page 12 of the reference tables. All right, first one. So we've got a dry bulb temperature of 0. So we're going to find 0. Okay? And this is relative humidity, so we're on the bottom chart. And we have a difference of 5. So let's line up 0 and 5. Looks like we've got 11% relative humidity. We've got 5 and 0, so let's find 5. Ooh, that's not going to be great because it goes up by 2s. So we're going to have to look between the 4 and the 5 and use that solid line to help us estimate. Looks like we have a difference of 5. So temperature of 5 and a difference of 5. It falls somewhere between 27 and 35%. So let's put 27% to 35%. And now let's look at the next day. We have 10 and 5. So 10 is our dry bulb and our difference is 5. So it looks like we have a humidity of 43%. Last column, we've got 15 degrees. So again, we're going to have to look between the 14 and the 16 on the reference tables. And we're going to have a difference of 5 again. So we come out here, and it looks like we have a relative humidity between 50 and 54%. Now we have some data to compare and contrast with. So let's reread the question. According to the data shown in the table, which day had the highest relative humidity? I think it's obvious after you put the data down that we're talking about day number 4. So number 2, what is the relative humidity when the dry bulb temperature is 16? Dry bulb 16. Wet bulb temperature of evaporation is 10 degrees C. So we've got 16. Let's go. We're looking at relative humidity. Make sure you don't get confused which chart you're using. Okay? So 16 degrees C, we find that row right here, and we've got a wet bulb of 10, but remember we're taking the difference, so that's 6 degrees Celsius difference. We're going to find that column, see where they line up. I'm finding 45%. All right, so now the rest is up to you. I am around. Text underneath the video, leave a comment, leave a question, go on Google Classroom, leave a comment to your question. I know these videos are rather lengthy. I appreciate if you're watching them and you're going step by step in order to help you understand what's going on. Feel free to send a message to me, and maybe I'll communicate a little bit more through WebEx so that we can understand this maybe a bit more live instead of it just me being a recording. So thanks again for watching. I hope you got something out of this. Feel free to rewind. Thanks. Bye.